Hello, everyone. Good morning. So I'm Akhil Arora, a PhD student affiliated with the Data Science Lab at EPFL. So today I'll talk to you about how well and under what scenarios can we approximate Wikipedia reader navigation behavior using synthetic data that is generated from publicly available sources. This is joint work with Martin Gerlach from the Wikimedia Foundation, my colleagues from the Data Science Lab, and my advisor, Bob West, who also happens to be one of the co-organizers of AMLD. Okay, so while users browse any website, they leave information-rich traces of their navigation behavior, which further tells us how these users actually interact with and consume the content offered by the website. In the context of Wikipedia, these traces can be seen as depicting the learning pathways that these users take while browsing Wikipedia. Naturally, the insights into navigation patterns have high utility because they can be used to understand and better serve readers' needs. They can be used to mitigate knowledge gaps, or they can also be used to organize even a curriculum for the readers, which will only improve their learning experience. That said, despite so many interesting practical applications, there are fairly limited studies that systematically focus on understanding reader navigation on Wikipedia. And this is because of one key challenge. In the effort to ensure the privacy of their readers, the data, the actual navigation trace data, is held private by the Wikimedia Foundation. And this is a very critical thing because Wikimedia Foundation doesn't want to basically destroy the privacy of their readers. Thankfully, there is a publicly available resource which is called the Wikipedia Clickstream data that actually extracts the count of referer resource pairs that is extracted from the very privately held navigation trace data in the servers of the Wikimedia Foundation. Intuitively, what you can think of is that it captures how many times did readers of Wikipedia went from a page A to another page B. So as you can see from this particular graphic here, you can see how many times did users of Wikipedia went from the page London to a specific page England. So this can be seen as somehow capturing the navigation that's observed in the first hop neighborhood of the network. And to further ensure privacy, what's done is that every transition, which is like rare, and here the threshold is something that occurs less than 10 times, is also omitted from this data. So while this is good news that there is a publicly available resource that helps us understand how people navigate, another key challenge here is that the next page visit, as we can see from this data set, only depends on the current page. In other words, it only captures the first order reader navigation behavior. So in the rest of the talk, we'll just think about to assess the utility of the Wikipedia Clickstream data as a resource to study reader navigation on Wikipedia. And we focus on two key research questions in this context. One is, how different are real navigation trajectories from those that could be generated synthetically via the Wikipedia Clickstream? Second is, how well can we approximate reader navigation via such a resource that's the Clickstream? So to answer our research questions, we look into 4 different types of synthetically generated data sets, which are described here in this table. And just talking a bit more about generation, right? You can see there is one key similarity among all the synthetic data generators, that they are only looking into the first order reader navigation behavior. That is, they follow a Markov first order process. One key difference that can be observed in these generators is that the transition probabilities that are used to govern the random walkers are different because they are derived from different sources of information. So in the interest of time, today we're only going to discuss about 2 specific analyses that we conducted in the paper. That is, first, the mixing of flows, only because of its intuitive appeal. And as we'll see, I'll talk about it, you'll see how intuitive this is. And the second part is a downstream task, which is typical in the context where navigation data is available, which is the next article prediction. So in this specific analysis, what we do is we look into all specific trajectories that pass through a given article, which can be considered as this article in the middle, right? And what we do is we connect the source and the target pages. And now we want to understand whether there exists any predictability, like that is saying, if you have the knowledge of the source article, can you reliably predict what the target article is going to be? And as can be seen from the plot on the left side, right? We govern this by a concept we call mixing of flows. That is, how much does the incoming traffic into this fixed page differ from the outgoing traffic? And as can be seen on this right plot, right? Having the knowledge of the source, you can with high confidence, you can predict what the target is going to be, right? So the idea here is, how can we measure this predictability? And we capture this via mutual information, which basically quantifies, which basically tells us how much does one random variable tell us about another random variable. And in this case, how much does the knowledge of the source actually tell us about the target? And if you think about an extreme case here, right? If these events are independent, one can think of that there is the mutual information will be 0. And in that case, what will happen is that this will exhibit a strong mixing. That is, there is no predictability. So, and this is what we observe, right? So the mutual information is close to 0. And in this case, where we call this case as a weak mixing, the mutual information is high, and there is strong predictability. So the point here, what we are trying to make, these are anecdotal examples, but the key thing what we did was to even analyze the distribution of mutual information measured from different real trajectories for different language versions in Wikipedia. And we found that this is, in most cases, the mutual information is close to 0. That is, the traces actually lack predictability, right? And it's important also to see that this is an exponential decay curve, where you can observe that it decreases very fast, right? You can see that less than 10% of pages have a mutual information which is greater than 0.2. In fact, only less than 0.1% pages have a mutual information greater than 0.5. And going back to this anecdotal example, what we can see is that, well, the specific thresholds are not important, but the higher the mutual information, the better the predictability, and the weaker the mixing. So this is one key finding from our study. Another key finding was looking into a specific downstream task. I'll just explain the setup here, right? So we look into the basic task of next article prediction. And just to, and in the previous case, while our goal was to look into only the real trajectories and try to understand it from, what are the basic characteristics there, here what we see is we look into different types of data. So we compare the real trajectories with the synthetically generated trajectories. And since we know that the synthetically generated trajectories actually follow a Markov order 1 process, and the real data may or may not, or actually may follow a higher order process, we specifically train a model on a very limiting case. We just want to see if the real data is Markovian or not, or maybe if there are higher order patterns that can be found in the real data. So we train a Markov order 2 model with inputs S1, S2, and T, and we then try to assess the rank of the true target in the rank list obtained via the inferred probability distributions. And we evaluate on a held out test set using mean reciprocal rank. So the key findings here are, again, that, well, the real data, which is depicted by the tag logs here, actually performs the best, and the differences are statistically significant with the next best result. But the key finding here is the publicly available data sources actually are not that far from if we the models which are learned via using the synthetically generated data. They're not far from what we do when we use the real data. So, and importantly here is what we observe is the performance difference is higher for low resource languages. And this, we pros and hypothesis here that for low resource languages, the effect of ensuring k-anonymity by restricting to only transitions which occur more than 10 times play a larger role than the restriction to the first order. And this can be actually explained using this results on the filtered queries, where you can see that the difference between the private clickstream and the public clickstream actually goes away. And this is primarily that the way we do it is we only restrict to those queries which were actually observed while training the model. So moving on here, it's basically a summarization slide, and the goal is not to overwhelm the audience with numbers, but what we want to show is that in most cases, while the differences are still statistically significant, but the effect sizes are within 10% in majority of the cases. Okay, so moving on to the takeaways. The first important finding here is that real trajectories exhibit strong mixing. That is, mutual information close to 0. And there are very rare cases where the trajectories portray a larger mutual information. That is, these highlight cases where real trajectories differ substantially from the synthetic ones. The other important point here is that the clickstream data performance is usually within 10% when compared to models trained using real trajectories. And the important part here is that we also trained what we call as navigation embeddings, which captures the behavior of the users. And we observed, and because the properties of these embeddings were measured by looking into the performance that we can see in these downstream tasks. And what we observe is that these embeddings are quite close to each other in terms of their performance. So we can still learn behavioral embeddings by just using synthetic data from Wikipedia. So this work actually gives quantitative evidence, and this is the first ever such study which actually gives quantitative evidence about the utility of Wikipedia as a publicly available resource that can closely capture reader navigation. Naturally, this work has large implications where there are many cases where clickstream data sets can be considered to be good enough. Right? And what we mean by that is that research now on Wikipedia navigation becomes accessible to a wider audience. In fact, the Wikimedia Foundation team is now working to make clickstream data sets available for almost all language versions. Currently, they're only available for the 11 largest languages, but now they're trying to, with this finding, and since we have the luxury of collaborating with them, they are right now working to maximize the coverage of clickstream data across different projects. And then this also bolsters user privacy because there is no need to store or reveal sensitive data when it's not needed. So that said, we are not saying that this is a panacea, right? We're not saying that you can just use synthetically generated data and you don't need real data at all. There are many cases where clickstream data is not good enough. And for instance, if you want to do some type of user modeling, or you want to understand how information consumption patterns of readers actually vary, right? In those cases, you might need to have access to their geolocation or the timestamp when they started their sessions and things like that. In fact, there is already a paper from our lab under review which actually discusses about about these things in more detail. And the broad impact here is that clickstream-like data can actually empower research on online platforms beyond Wikipedia, right? While there is still an open question that whether our findings will generalize to data sets beyond Wikipedia, but that's an interesting question in its own right, and I think we should, the community should focus on studying these type of questions a bit more. So eventually, this is an encouraging call to the community to release such data sets wherever possible and make navigation on online platforms accessible to a wider audience. With this, I'll just point you out to this. You can scan this QR code and go to the web page that describes about the clickstream data from the Wikimedia Foundation. If you want to know more about the code and data sets that were used for this specific study, it's available on GitHub under the DLab GitHub organization. And if you are interested in the preprint of this paper, you can also look at that. So thank you. And these are the coordinates via which I can be reached. And that's it. Thanks for your time.